It's really an honor to interview you, Andy, and to welcome you back to Berkeley. I don't know if you remember, but I think the first time we met, I was a beginning grad student here in 1981, my first year, and I think you had at the same time arrived as a professor in computer science.
Yes.
I think that these were really interesting times here in Berkeley, in the early 80s, and I wonder if you can tell me, your experience of Berkeley from that time, both scientifically, but also in other ways.
I think coming to Berkeley was quite an experience for me, especially at that time. It seems that Berkeley is a place where the young kids are running wild. I think partly because at that time, the age of the modern cryptography was just starting. Mm-hmm. And Berkeley was the center of action in trying to formulating exactly what the modern use of cryptography would look like. Mm-hmm. So I was fortunate enough to come here at that time and able to take advantage of this complexity-based cryptography, which turned out to be a very big thing. And I got to know many of the shakers and movers here, and I really benefit from that intellectual venture at Berkeley. And of course, at that time, I think the most wonderful thing is not just the scientific work, but actually getting to know so many of the future great scientists there, including Umesh, yourself. And over the years, that my own research field actually, in many ways, were influenced by the people that I know at that time. And I remember that my encounter with quantum computation was actually inspired by you when you visited Princeton University and told me about this great thing of your work and what Richard Feynman had started. So that got me interested in starting doing work in the quantum computing myself. So I think that Berkeley, in many ways, played a big part in my scientific life and also in my personal life.
And definitely, in a very big way, vice versa, you played a huge role, even though you stayed for a year here at Berkeley. But that was a pretty emphatic year. So I just wanted to go back and see, when you arrived, you had the right tools and the right viewpoint to take advantage of this wonderful setting here. So can you describe, what was this training and tools and so on that you brought to the table that were so interesting?
I think perhaps a large part was my training as a particle physicist, mm-hmm. and where the philosophy and the way to view the science was somewhat different, mm-hmm. from that in computer science. And in physics, the important thing is very pragmatic. You really want to explain phenomena, you want to solve problems by whatever means you have. Mm-hmm. And mathematics is only one way of doing it. So in a way, for a physicist, the theorem statement is much more important than the proof. Mm-hmm. And so I think that I was very deeply influenced by that tradition, and therefore when I started doing computer science, I still had that in mind, namely that I would want to find what was the essential science behind it. And it's not just trying to find a good statement and try to prove it, but really how to interpret it and the spirit of it.
I see.
And I thought that I think that kind of approach made it possible for me to explore in some directions that was not usually taken by people who were just trained in mathematics or in computer science.
Mm-hmm. Yeah, it was very interesting. I remember the course you taught that first year. I found it very very stimulating. Probably exactly for the reasons that you said. But of course, when you say that you weren't so much into the proofs, but the statements, it's ironic because there are many proof techniques that are really identified with you. There's Yau's lemma for there's the hybrid argument which you used in your pseudo-randomness. They are just a sequence of techniques that you also brought to the table.
Yeah, well, thank you. I think that by hindsight, by the present standard, I think that all those techniques were pretty elementary. But I think that what you said has some resonance in my thinking, namely that basically when I kind of envision a certain result, and I spend all my energy in trying to prove it, and I didn't care about the elegance of the proof. I only wanted to find some way of making it happen. For example, improving asymptotics. When I think about big numbers, I say that I put the n to the 10 to the 100.
Yes.
So I think that when you are free from the constraint of the standard of elegance, and you will be able to do things sometimes more effectively. Namely that when I prove things, usually, well, perhaps it's not so much different from yours, but let me say it from my viewpoint. Namely that I would like to map out the proof in really a big way, and then a lot of things I would just take for granted that it could be filled out later on.
Yeah.
And so in this way, I think I'm a little bit more bold in that fashion. So when I told my wife saying that I think I have proved the theorem, actually I think I would be very far away from proving it by the standard that usually we have in computer science. And I wonder whether you also have that kind of organization when you try to prove some theorems.
Yeah, well, definitely. I start with with a feel that something must be true, and then try to get go at it. Probably more top down. That's what you're describing. It's a more top down process.
Yes.
Yes, very much. And I think this is this was some a reason why when I found your work so appealing. Actually.
Yeah, I think there is some sort of rawness in my thinking, and I usually have difficulty after I prove a theorem, try to write it up in an elegant and a precise fashion, because a lot of things were done in an intuitive way, and then using a kind of patch-up style of making the proof to be barely passing the rigor test. And a lot of times I would get I think because in my youth I think that I have this aggressiveness in work. I very quickly lose interest in what I have proved, and I would be much more attracted to something that came into my attention.
Mm-hmm. Yeah. So, just going back to something you said earlier about getting the right definitions and the right formulations. So that's something that you did, there are several instances of that in terms of pseudorandomness, just getting the right definition of what it meant to be pseudorandom, this indistinguishability from truly random, or this millionaires problem, of defining the problem, of two millionaires trying to compare, their wealth and without letting the other person know anything other than the direction of the inequality. So it seems like this has been something that you did consistently in terms of finding the right statements.
Yes, I think I think basically you and I are alike in that fashion, that we would like to go down to the basics, mm-hmm. and would like to find the question and to try to extract the essence of the most critical and fundamental notion, mm-hmm. of what we are trying to capture. And so I think in that fashion, we are more like natural scientists, mm-hmm. that actually treating the subject as a field of natural science, and so it's no different when Darwin was trying to understand exactly how the world came about as it is. So I think that, in a way, certainly speaking for myself, I would try to read it and try to understand phenomena, and also to understand the difficulty of formulating exactly what something is. For example, like in pseudo-randomness, because before I proposed that definition, I think people have different ways of thinking about what pseudo-random number means, because it all started with the statistician mm-hmm. of having all these tests. And when computer scientists came along, computer scientists formulated some notion of pseudo-randomness because they needed it in order to solve some particular cryptographic task. Mm-hmm. So it was, I think, from a physicist's point of view, you really want to understand, not having a notion mm-hmm. which depends very much on what kind of purpose you have. Right. But instead, you would like to have a all-encompassing notion so that it would apply mm-hmm. to all kinds of places where you would need this definition.
Mm-hmm. So moving forward, it seems like one thing that's happened, these notions like, distinguishability from, polynomial time indistinguishability and so on, these have been built upon, there are these vast structures that have been built upon it, and theoretical computer science at this point, it's become very sophisticated, as you said, in terms of proof techniques and so on. But is that, and that's a great enterprise moving forward. But where do you think that this more, this approach that you described in terms of studying things as a natural science, where do you think that fits into the future? And do you have advice for young computer scientists or older computer scientists in terms of theoretical computer scientists in terms of what they should, how they might think about questions?
I think I think a field has a life of its own.
Yeah.
So if you hit the right subject and you started to introduce some concepts, and later on the field developed and many people have done wonderful work in it, then I think it finds its own way into where it can be applied to and becomes a big enterprise. I think that that exactly what a young person should do and at what stage that one should get into this game has a lot to do with a person's temperament and the technical background. For me, I am much more attracted to the initial stage of something, namely that to try to translate a situation when it's sort of chaotic, that in an area where there seems to be great potential, but there's no systematic account of the subject. I think I like that kind of at the beginning, and plays some role in transforming it into something resembling an order, so that it's suitable for further investigation. So that's what attracted me most. But there are many great scientists who are good at in the middle stage, where to make things to acquire more generality and more elegance and more applications. I think that it all depends on what you want. So my suggestion to the young scientists would be that you should experiment with what you can do. I think when you are young, you really should let your imagination and your enthusiasm run wild. That you should not care. You should not care too much about your health. I think that you should get up very early and start thinking about problems until when you go to sleep late at night. And I think that during that whole time, you should go to many talks and you should try to solve problems that you can understand and that interest you. And it doesn't matter whether it fits your overall plan. I think that you should just try a variety of things, and at some point you will start finding what you are good at and what you are most enthusiastic about. And when those things clicked, then you are on your way to do something really significant.
You know, it's very interesting. This was probably almost exactly the same advice you used to give 35 years ago. You know, about
you remember that?
You know, it struck me at that time that you used to say, well, you know, as a young graduate student, you know, it says you should really work on as many, you know, just work on different things and you know, just go wherever you're, you know, whatever strikes your imagination, you can do one thing later. There was another thing I remember you said at that time, which was that you knew a few things really well. You didn't know that many things, but the few techniques that you knew, you really knew them extremely well, and then you applied them in many places. So do you remember?
I probably have said that, and I think it's true, and it's not just for myself. I think that almost everyone has a limited number of tricks that one is particularly good at.
Yeah.
And so I think it's true as ever that you shouldn't be too envious of other people's ability, because what I have encountered many great geniuses in my life that I think in almost everything there's somebody who can do it better than I do.
Yeah.
But I think I can still find my place in the world, because there's always some combination that because I mean nobody has the time to solve everything in the world.
Some time ago, 10, 15 years ago, you went back to China. Can you describe, what that's been like for you and where things are going now in China in terms of your institute there and how you see it moving forward, or what you've been trying to accomplish there?
Yeah, I think that going back to China, I think it's a very exciting adventure.
Yeah.
I certainly did not know exactly what I would do in the ensuing 15 years. By hindsight, it's a pretty difficult process. And I may not have the courage of trying to do it if I knew all the things I need to do. But it's a very worthwhile journey. When I first went back, main purpose was really to try to bring my knowledge and experience and to educate the undergraduate students and perhaps to establish some theoretical computer science group and turn out good graduate students in that particular area. But over time, I started taking on much more than my original intent to do. And I started a elite undergraduate class called Yao class now, and it's very successful. And I started a quantum lab, so hiring physicists to build quantum computers. And now, after 8 years, it already became one of the leading labs in that area. And I also, at the same time, started an institute for interdisciplinary information sciences. So this allowed me to in some way, realize my dream of combining all the applications of computer science together in one place where people can interact in a very intimate way. And so over the 8 years for this institute, the first group of people that I hired turned out to progress very well and are now getting tenured. Really, I was surprised that after a few years, I suddenly realized that they know more than I do in many ways. So I'm very happy with what I've been able to do. So I think in some way, it's very exciting because I think it's the kind of opportunities that I would not have been able to do had I stayed in the United States.
Mm-hmm. So do you get time to do research, or do you?
Yeah, I thought it's pretty important to keep one's research work, no matter how busy you are. Of course, I think there are periods of time when you have to devote a lot of more time to the other aspect. But I think over the years I still keep my research going, and also keep my spirit in the sense that I have always wanted to do new things, and so enter into new fields. And in the last 5 years, I entered into this area of mechanism design and auctions, and now into blockchains. So I always find it exciting to enter a field, as I mentioned before, that something I know is going to be great, but it needed people to, especially theoretical computer scientists, to solve problems in it.
Tell me about, I guess, what's now called ITCS, but was called ICS. The first, the conference. I guess the first 2 or 3 years it was held in China, and I think you helped launch it. There were many people who felt there should be a new direction for conferences in theoretical computer science. I guess that somehow, in some ways, it ties into this whole notion of what are interesting questions to work on, or what the goal of theoretical computer science should be, or at least what one of them should be.
Yeah, I think that this new conference indeed was started in China. That the first two times it was held in Tsinghua, but later on it became very international, and now it's taking place in different continents. I'm certainly you're one of the people who co-founded this conference with me, and I think that our original purpose, we all agree, is that that we should kind of return the theoretical computer science to its roots in some way, because I think as a field becomes too successful and become too systematic, and have all sorts of regulation, and this you cannot do, that you cannot do, and so on. I think it's a necessity when something becomes big. But on the other hand, I think that we were all worried at that time that the field is losing its vitality just because the conferences becomes too big. That it's very hard to keep the original character, namely to be able to get ideas out while still in its primitive stage, because the referee's comment can also be saying that, well, this is a little bit too preliminary, and maybe you should wait until it gets more solid. But actually, I just don't agree with the that kind of approach, because it become more too much like an enterprise. Yeah. I really like science is done as a result by individual scientists, and we can all present things in this most original form, and because that's the form which benefit people most, because you let people see your innermost thought in its original way, and because that's where all the vitality is, the process of transforming kind of problem in an undefined form into a mathematical form, so that its conclusion can have an impact. I think that's the process that I think if I were watching movies, I think those would be very good movies for me, instead of movies which become too much polished.
Yeah, I see. Right.
But maybe I should ask you that.
No,
I think,
in some
I think that you have been, that especially you are now chairing that conference. That conference. How do you think
I really like the way you described it. This whole notion that things that are too polished, I mean, they're extremely nice to see, but sometimes what one values is how did it emerge, and the original ideas can be even more powerful. And so, if you can grasp those, that's why sometimes when I used to go look up in the old days the proceedings of Stock and Falk, those proceedings papers which were much shorter, unpolished, much more preliminary. I found those much more interesting to read than the final journal papers. Sometimes, they obviously serve different purposes. So, I really like that thought. Actually, you were talking about the state of that you were worried about the state of theoretical computer science back in those days. That it was getting too polished. So, what do you think now about the state of theoretical computer science, and also about, how vital is it? And
I think there are different ways of looking at it. Yeah. I think that one way of judging the success of a field is that how do people in that field, do they like it the way it is, and they think that they are doing the right thing and the most approving things that they like to pursue. I think from that respect, I think the field seems to be doing well in that respect, because I think that that people are still very enthusiastic about going to these flagship conferences and really treasure the acceptance by these conferences and present their work. And so from that regard, my suspicion, I haven't talked to many people about how they feel. From looking from that perspective, perhaps it's okay. It's and also serve the purpose. I think that those conferences still have a prestige that are recognized by the administration in computer science in general. But for myself, I think it would not be the right forum for me to continue to publish in those conferences. I think that people demand too many details. That nowadays, if you have to prove everything to every epsilon and delta, so that people at least have a chance to examine it. I'm not so sure that a great conference needs to be that squeamish about saying that we never make any mistake. And I think it's a error correction process. I think that I think if you look at the early days of quantum mechanics and you look at the great people who have published papers, I think many of them, by hindsight, probably would be wrong in their interpretation. But it's precisely because of during those kind of effort that people come to understand the essence of the world in quantum. I'm not sure right now the process that we have through these conferences it's a way to achieve that purpose. But on the other hand, I'm sure that when people have private contacts, I think that they can get those kind of interaction away from the conferences. For example, every time I talk to you, it's particularly delightful because I think that you always present your latest work in its most primitive form. It's something that show exactly the essence of the problem, and I really enjoy.
Thank you.
Those kind of insight. So I would hope that the conference that we started will serve that purpose. I haven't kept track of it recently, and I assume that it is fulfilling our original conception, and I'm happy that because I think in the beginning we were also debating. It wasn't that easy to come to a consensus when you have some very intellectually powerful people. I think that what comes out in the end, I'm really happy. I hope it will continue to serve as a forum where one can see that the continents get formed, the stars get formed. I think that I really would like to see those kind of things, the raw evolution of ideas in conferences.
So one theme that comes up in what you've been talking about is these fields which are which were at their they were in this early stage when they were as they are being created and creating the right paradigms and the concepts with which to think about them. This is something that has always interested you, and so was that more true in the early days of computer science? Going back to the early when you were in Berkeley in the early 80s, and so on? Or do you see, do you see that even today, after computer science is so developed that there is a role for that, or is there a big role for that now, given how much computer science is evolving and changing and exploding and so on?
Yeah, I think it has a bigger role. I actually think the opportunities are better than 30 years ago when I was at Berkeley.
Yeah.
I think that certainly in the 1970s, when I first entered the field, there were few opportunities for free thinking because there just wasn't enough material that you can be creative about. But as time goes on, I think the 1980s, suddenly things, I think the 70s, it was still in the process of continuing the Alan Turing's, this undecidability. To make it into the complexity realm, but I think the real excitement in theoretical computer science came about, as far as I'm concerned, is that when technology progress became important into the thinking of theoretical computer science. Yeah. In the early 1980s, I think there was a seismic event, namely that suddenly the mainframe really is getting to be relegated to a secondary role, and because the distributed computing and personal computer came about, and suddenly we can think about network, we can think about even electronic commerce. There were far-sighted people who thought about it, and that led to the development of many things. For example, communication complexity was one of them. As I tried to do it, and the cryptography, the Diffie-Hellman public key, it's a way of reacting to technology, and also in distributed computing, people thought about how to build reliable distributed systems. And so all these intellectual questions suddenly arose. There are just myriads of such problems, and each of them has very, very kind of a deep has a very deep meat behind it. Yeah. So that it would take people decades in order to make progress and solve them.
And you see more such questions in the future?
Exactly. In the 1980s is the distributed computing, and in the 1990s it was computational biology. Suddenly, the computer science becomes important, and I think it was a very excruciating process of trying to create a interdisciplinary field, and finally I think that people succeeded in bridging the gap, and then in the early 2000s there was this algorithmic economics, the mechanism design, and because the Google and the Baidu, they were they need to have ads option. And so that's another impetus for computer science getting into it, and not to mention quantum computing. I think that you are one of the probably the earliest computer scientists who ventured into that area, and so that's another thing. So we see that every 10 years something big comes along, and usually serious scientists sometimes say that, oh, it's just a hype, right? But that's not true. That anything that has a hype in it, usually there is a big potential science that is related to it, and like the AI, and I think that there's this waves and waves of technology change, that we are lucky to be computer scientists, and we have the really very, our change in technology is many, many times faster in most other scientific areas. And so we get to take advantage of the technology change, and we put our theoretical expertise in it so that to take full advantage of the area. And so I think that it's really the most interesting time to be a theoretical computer scientist. And earlier today we were talking about many fields seems to share some commonality, and eventually there might be a kind of a common discipline of the real theoretical computer science. I think that we should go to that land. I think that computer scientists should move en masse and just drop what they are doing today in most cases, and do something new, because I think that you find more reward. That's my opinion. I'm sure that there will be people will not like it.
Well, on that optimistic note, well, it's been a real pleasure hearing your views.
Enjoy speaking with you.
Thank you.